Hello, everyone. This is Group 4, and we are presenting on human crowd phenomena. My name is Richmond Buckman, and then we have Kudli Obiakor, we have Toffa Taylor. So I would love you to take about 10 seconds to analyze what we have here. As we can see, we have a lot of people, some in pink, some in white, kind of overcrowded area. Yeah. So with our project, we are basically to analyze this dense crowd and then to develop or to come out with a model that will help us to numerically calculate the critical conditions, which will help us to avoid or to reduce stampedings. And then we know mostly in a crowded area like this, of which I would love to cite an example, during the World Cup 2022 final between Argentina and France. Remember, there was a video from Argentina that we had a lot of people that gathered in a particular place to watch the match. And I mean, in this scenario, we want to also use this scenario to help us understand whatever that we have here. Now, we can say that, I mean, in those situations or in a place where we have a lot of people that are gathered with I mean, they are excited, moving around up and down, we can clearly say that there are uncontrolled collective motions, and which sometimes lead to compression among the gathered people. Yeah. And so we analyzed this scenario, and then we came out with a model again, to test the robustness of our model, we calculated the critical parameters using our model, and then we compared them with the data that was given in the reference material for this project, of which we found out matching, and that made our model a good one. We actually loved it. So now our project is, as stated earlier, we are going to look into three sections. We are going to look into the mass balance,
because
and then again we also looked into the momentum balance, and then lastly, because we have a lot of people in a crowded area, we considered that we related the people to like molecules in order to see how that relate, and then I mean making reference to what we've learned in class. So on mass balance, we will begin with the mass balance, then move to momentum balance, and then lastly the human fluid hybrid. Now, with the mass balance, we want to define some terms. So first of all, there are some assumptions that we made in this project or in our modeling, and would love to let you know so that at least it will help us along the line. Firstly, we considered the movement to be a linear movement. So there was nothing like a chaotic movement. And as a result of that, we can say that the movement of the crowd is linear. Therefore, we can assume a laminar flow scenario here. Again, we also implemented here the boundary conditions in our momentum balance class that we've been doing. And then here we are considering a particular area. So we took a particular area as our reference. And then we are saying that at the boundaries, we have our velocity to be 0, and then our we are again saying, as said, our shear stress, that will be a maximum at the boundaries. Again, we are saying that our momentum is transported from a lesser region to a higher region. Now, when we consider the linearization, so with the linearization, we want to basically find the relation between density and velocity. And as we know, they are linearly related. So we are going to apply the linear equation, of which we have here as y equals mx plus b. Then we also have the relation between density and then velocity. However, let me define this term as we have here. So this is to give us an idea that we have a sum of people that are coming in with respect to the very area that we've selected. We have a summation of people that are coming in And then when we subtract the summation of people that are going out from it, we are going to get the accumulation that we have. And this accumulation is with respect to a particular time. So this equation we have here, we've summarized it to now this is our mass flow, and then it is related to density times velocity. So with the linearization that we were talking about, so with this expression, we can also relate this with what we have, as we can see here, velocity equals this. So this is basically our slope times the density plus our constant. Now we have here the crowd property. So with this crowd, we are saying that the density of the crowd is basically the people per the area that they occupy. That is the density. So me, Richmond Buckman, if I stand at a particular area, yeah, the very area that I occupy, of which it will be different from someone who is more slim than me, or yeah. So basically, my density might be different from that of Okudli Obiakor and then Toffa Taylor. Now with the velocity, we are saying that since there are movement, probably the individuals, they do carry velocity. Now this is our mass flow rate, of which we are calling it the flux of the crowd. So now we are considering the crowd. So now we are going to use this equations we have here. We are going to solve in order to get our velocity and get our density, and then again model it to find the critical values for that of density, that of velocity, in order to make decisions as to the very thresholds that we have whenever we have a number of people like this that have been gathered in a place. So we will use those values that we will get to advise that in scenarios like this, as to the number of people that are allowed to be in a particular place, and then in order to reduce or to avoid stampedes. However, again, we are saying that there can be further refinements of these assumptions, may be necessary to enhance the accuracy of our predictions in varied scenarios. And then we hope that after you are done watching this video, you would love to consider other scenarios like a chaotic case to help modify the model. And additionally, probably we can also incorporate real-time data that could provide more profound insight into the dynamics of crowd behavior, and then improve the model's applicability in practical situations. So now with the boundary condition, let's go. So now, as stated earlier, now we are saying that the density equals 0. If the density is equal 0, then we do have our V to be V max. And then if our density equals density max, we are saying that V equals 0. So we are going to input these boundary conditions into our equation that we'll solve for. Yeah, great. So now when we input all these boundary equations, we are going to get our C to be V max, and then we are going to get our slope to be minus V max over density max. Now let's go ahead and solve for the velocity. So now solving for the velocity, we know that V equals V max, right? Yeah. So we fix it into the equation that we have here. All right. So as we had here our C, and then we had here our M. Now we are going to substitute these that we have here into this equation that we have here. So that will give us this expression, V equals minus V max over density max times the density itself, which is here now, plus our constant, of which we found out to be V max. Now, if we want to make, we just want to simplify the equation. Now, simplifying the equation, we are going to get our V has to be V max into bracket 1 minus density over density max. Now, let's go ahead and solve for the crowd flux. So with that, what we are going to do is that we've already calculated for our V. So we are going to substitute this V into the expression we do have here. Now, when we substitute this, going to be the expression, we have our mass flow rate equals to our density times the V expression that we had. Now simplifying it, we are going to get this expression we have here.
Okay, I should continue from where Richmond stopped. Initially, we derive an expression for the flow rate. So in these slides, what we are going to do, we are going to find the expression for the critical density, critical velocity, and the critical flow rate. So from the previous slides, we have a Q being equal to density in bracket Vmax minus density times Vmax divided by density max. So at this point, at maximum flow rate, delta Q over delta density is equal to 0. So what we are going to do, we have to differentiate this term and equate it to 0 and simplify the expression that we're going to have. So differentiating this term, we now have Vmax minus 2 density Vmax divided by density max is equal to 0. Making Vmax the subject of the formula, we now have 2 density Vmax divided by density max. And simplifying further, we have Vmax on both sides of the term here. Cancelling Vmax out, we now be left with density max is equal to 2 density. And I'm making density the subject of the formula. We now have density is equal to density max divided by 2, which is equal to the critical density, as we are trying to find the critical density and velocity. So for the critical velocity as well, having gotten the expression for velocity in the previous slide, what we now have to do is that for the critical velocity, the expression, wherever you see V, it will now be Vc, and wherever you see density, it will now be density C. So what we are going to do now, we are now going to substitute the value of density C here, as we can see from here, which you have gotten to be density max divided by 2. When you now substitute the value and cancel out, this particular term here will give you half, and 1 minus half will give you half. So at the end of the day, we now have the critical velocity to be Vmax divided by 2. Then for the critical flow rate, initially from the previous slide, we have that for the previous slide, we have that flow rate is equal to density times velocity. So at critical points, or considering critical flow rate, it should be equal to critical density times critical velocity. So which is what we represented here. It can be represented in 2 ways, either by using the previous expression and substituting the values, or writing QC is equal to critical density times critical velocity. Okay, so in these slides, we have gotten the critical density, the critical velocity, and the critical flow rate, which is what is represented here in this bracket in yellow. So our aim here is to find the actual values of the critical density, critical velocity, and the critical flow rate, and compare it with what we have from rate ratios. So from rate ratio, for the kind of crowd that we are considering, the density maximum is equal to 9, and velocity maximum is equal to 0.8. So using this expression, the critical density is equal to critical mass divided by 2. Talk with your neighbor, solve for critical density, and tell me what you're going to have. Remember to include your units. I'm giving you 5 seconds. Okay. So with the formula, it will now be 9 divided by 2, which is equal to 4.5 people per meter square. Then for the critical velocity, using the formula above, which is maximum velocity divided by 2, it will also be 0.8 divided by 2, which will also give us 0.4 meter per second. Then using the formula above, given here, critical flow rate is equal to critical density times critical velocity. Work with your neighbor, calculate the critical flow rate, and include the units. 5 seconds. All right. So if you have 1.8, you are correct. So using the formula from the previous values that we got, critical density is 4.5, critical velocity is 0.5. So from our formula, we just have to multiply both of them, 4.5 times 0.4, and that will give us 1.8. Then the units, people per meter seconds. So these values that we got here correlate with the rate ratio values, which is being shown here. Comparing from rate ratio, we got 4.5 as the critical density. From rate ratio, we got 4 plus or minus 0.5, which is like having a range of 3.5 to 4.5. And they also got a critical velocity to be 0.35 plus or minus 0.5, and we got 0.4. So it correlates with what they have in the rate ratio. So what these critical velocity and densities are like the set points which we are going to enter in the sovereign system at the particular point that we are going to, we are trying to control the particular situation that we are going to control the computerized system, so that whenever the density or the velocity of the cloud is getting towards these critical points, a sensor alarm will alert, and proper management strategies will be administered with the control team. So this is the essence of developing this model, now to make sure that the amount of people in the field at that particular point in time doesn't lead to generating a lot of pressure that will lead to stampede. Okay, we are now going to the momentum balance section, and the essence of this section is to monitor the movement between the people inside the cloud. Remember, initially the most important aspect is the mass balance, because we are trying to control the amount of people in the field at a particular point in time. Then with the momentum balance, we are now trying to control the friction between people in the field. But if you have effective mass balance control, the effect of momentum will be less because of less pressure force and all that. So for the momentum balance, from Newton's second law, we know that force is equal to mass times acceleration, and relating this in terms of momentum, total external force can be the force of the walls, force resonating from the people in the field. This is equal to derivative of mv divided by the derivative of dt. We use partial derivative in this case. So letting your right hand side in terms of our molecular and convective external force, just like we did in our lecture, we now have this expression. So this part is the molecular part, and this is the convective part. So in this case, we are made some assumption that we assume the people to be in a control volume, just like a gas molecule, a fluid molecule in a control volume. So in this case, the volume is going to be constant, and we assume that the movement is not that too chaotic, so the rate of change in momentum per time is approximately equal to 0. So in this regard, the molecular component will be 0, leaving only the convective component. So after that, we now have to simplify the convective component. So what we did next is we have to divide both sides by the area, and we all know that force over area is the pressure, and integrating delta A divided by A, integrating delta A we give you A, and dividing by A we cancel out. So we now left with P is equal to density times V squared. So for the critical pressure point, having calculated the critical density and critical velocity, what is P at the critical density point? Just talk with your neighbor, discuss, and tell me what you think about this, or what the expression of the values will be like. Okay, so the critical pressure will be equal to the critical density times critical velocity squared. And substituting the values that we have gotten for critical density and critical velocity, that's 4.5 times 0.4 square. We have the critical pressure to be 0.72. So this means that this particular pressure, beyond or at this particular pressure, we are now moving into a more chaotic situation, which we are trying to avoid. So what will happen at this particular point that the sensor alarm will blow, signifying the control system to control the exit or the entrance of people into the field.
Recall from previous lectures that we read this chart from Bird, Stewart, and Lightfoot, which shows us that gases' viscosities increase as temperatures increase, and gas viscosities increase as pressures increase. Pause for a moment and consider what circumstances cause people to act in various phases of matter. Imagine each person as an individual molecule. Do we most commonly resemble ideal gases, dense gases, liquids, solids? We considered people at maximum density to be liquid, and as dense gases at lower densities. At low densities, people typically avoid colliding into each other, behaving similar to ideal gases. In small crowds or in the hallway when classes get out, we bump into each other more often. When we wait in queue to enter or leave the Husky hockey game, collisions are more inevitable, more closely relating liquids. We've plotted the velocity and pressure for the density of people per square meter from a density of 0 to a max density of 9 people per square meter. We used Reynolds' equation and the assumption that Reynolds' number should be in the transition to turbulence, beginning to form some eddies at a Reynolds number approximately equal to 2,500, and set this to the critical pressure and density and velocity on this curve. From this assumption, we were able to back calculate a viscosity of 0.0007 meters squared per second. We felt that these assumptions were justified by the eddies of people which are visually identifiable in the crowds. In contrast to the previous slide, where people were considered as a liquid traveling across the surface, in the middle of the crowd, people are minded and want to stay in the middle of the field. And humans are more compressible than liquids, even if this causes physical distress. As the animated figure in red tries to enter the field, their z momentum is elastically transferred to the people in the crowd in the larger z direction. Their z momentum is also transferred in the x direction to other crowd members via viscosity. In order to perform this more complex momentum balance, we need to consider the momentum of the person entering the crowd, as well as the pressure and the shear stress that they exert on the field that they're entering. This is what we see in the start of equation with number 1. At z equals 0, as the person is entering the field, their height and width multiplied by the force on the crowd with the pressure and shear stress is equal to the momentum and pressure F when the shear stress in the ZZ direction disappears. We also need to find the rate of Z momentum across the surface at Z equals to L. And this is very similar, just on the very end of the field, how that momentum pushes all these people as the collisions act like dominoes and into an exterior wall that the crowd is confined into. We then combine these to find the Z momentum across the surface at x is equal to x. The Z momentum across the surface at x is equal to x plus delta x. Additionally, performing the momentum balance, we need to look at the limit as x goes to 0, or delta x goes to 0 for this expression, dividing the length that the person travels, their height and their width, and apply the pressure boundary conditions, Pz max and Pz min. We know that pressure is highest at the start of the motion, but as it bumps into the crowd, they're going, that pressure is going to dissipate longitudinally and laterally, reducing the pressure by the time it gets to the end of the crowd. Integrated across x, we can find the change in shear stress to be equal to this pressure, Z max, and the pressure in Z min times x over the length traveled plus an integration constant. And when we value this at x is equal to 0, we see that the shear stress is at its maximum. So we know that this C1 value is equal to the max shear stress. We can finally derive that the tau of xz is equal to the pressure in z at its maximum minus the pressure in z at its minimum times x divided by L plus the constant of tau max. Here are some of our references for the New York Times article that led us to the physics that keeps the emergence of collective oscillations in massive human crowds article that was recently published, and Transport Phenomena, 2nd edition by Bird, Stewart, and Lightfoot. Thank you.